Good morning, friends. Now, today we will see the design of stone columns layout, the numerical based on stone columns. So, how we can design the stone columns, we will see today in this lecture. Now, the design of stone columns layout by mainly involves the following steps. Number one, calculate of load capacity against bulge. So when the load is applied over the stone column, it will bulge. So we have to calculate in the first, that is the load carrying capacity against bulging. Second one is calculation of soil bearing. Okay, so what is the soil bearing against? So we have to calculate it. Next one is effect of surcharge. So what is the effect of surcharge over it? That will also we have to take into consideration. Fourth one is calculation of spacing. Okay, how much the columns are spaced. So these are the following four steps under which we have designed the stone columns. Now we'll come to that our numerical part. So this is a numerical which is of a stone column. I'll just read it out that numerical and then we'll move ahead for its solution part. Okay, a subsoil consists of a uh, soft soil, that is silty clay up to a 7-meter depth. So here the depth of the soil is mentioned at 7 meter. In situ undrained cohesion. Okay, this is a condition, that is Cu is 18 kilopascal, and addition data is given below. The weight density of the soil above the water table is 17.65 kilonewton per meter cube. Okay, so weight density of the soil above the water table. So I will just draw that one schematic diagram so that you can understand. See, this is a clay of depth is 7 meter. So here that if we have to draw the depth, so it will be 7 meter. Okay, so this is 7 meter. But what is mentioned? Effective density of that weight density, you can see weight density of the soil above the water table is 17.5 meter, and effective density below the water table is 7.85 kilonewton per meter cube on the above of the stone column of water table. Water tank is to be supported on earthen pad foundation. Groundwater table is situated at 1 meter below the ground level. So this is the zero level, ground level. This is the ground level. Okay. So this is ground level. Sorry, this is ground level. Ground level is shown in this way. I just erase. Okay. This is the ground level. Okay. So from here, that is 1 meter. Here you can see this is the groundwater table line. So I'll just show you that notation. This is a groundwater notation. Okay, so this is 1 meter. From here to here is 1 meter. This is 1 meter. Okay, so this total distance will remaining is 6 meter. Okay, so this is in this the soil is 17.65 kilonewton per meter cube, and here the gamma density of that effective density of soil is 7.85. Okay, so understood on the above stored column. So these are the all data which we have just Okay, you can see next one. What is that? Diameter of the tank is 79 meter. Over this pad, okay, this is the soil. Here is a one diameter, one tank will be um, situated, having the diameter is 79 meter, and load intensity from the tank and earthen pad is 147 kilopascal. This is the surcharge load over it, and the diameter of the stone column is 0.9 meter. Here the diameter of the stone column is mentioned in the question is 0.9 meter. Angle of internal friction is 50, and take NC will be equal to 6. Factor of safety against bearing. If we have to find out the bearing, then we have to assume that factor of safety is 2.5. What is asked? Design the stone column foundation system. So we move forward ahead. Okay, I think this is understood. So this is a actual diagram which we have already drawn. So this is a stone columns. Okay, this is not necessary that stone columns will be laid out in the uh, slant way. This is in the vertical way also. Okay, these are stone columns. These are the water tanks. Okay, this water tank diameter, yeah, from here to here will be, it will be 79 meter. This is a groundwater level. Here this dotted line is a groundwater level, and this distance is 1 meter above the below the ground surface. Angle of internal friction, you can see this is 15. Cu is given as 18 kilopascal. Okay, so I think you have understood this diagram. We'll move ahead for the numerical. So what is the note is mentioned in that numerical? The load capacity of the stone is given by addition of, first, the load capacity resulting from the resistance offered by the surrounding soil against the lateral deformation, that is the resistance against bulging. So if there is a this is a stone column, okay, if this is a stone column, and when we apply over it that load, it will bulge. Okay, when we apply the load, it will bulge, means it will deform in this shape. So when it bulge, so it is penetrated inside that soil. So the peripheral body where the soil is available, that will resist, and that force we will consider into our design. Okay. Second one is bearing support provided by the soil between the stone column. So here is the, this will be again, that is at the bottom there is a soil bearing capacity of the soil. So this, that will also consider. And the last, the third one, that is increase in resistance of lateral deformation due to superimposed load, due to surcharge effect from the surrounding. Okay, so here is the one stone column, another stone column, and in the same, at the same time, what is actually mentioned, increase in resistance. So what is this? This is a, actually you can see, this is a soil mass. Okay, if you can see in the 3D diagram, so this is the soil mass. Inside the soil mass, we will put that. I'll just change the color. We'll put the stone column. Okay, so this is addition, this much amount of volume. So by putting this stone column into it, there is a surcharge, and due to that again there is an increase in the load. So we'll take into consideration. So there are three types of load which we have to take into consideration. Okay. Okay. So calculation of resistance against bulging. So first step is yield stress on column due to bulging of column is given by this equation. So this sigma y will be equal to n phi sigma rho bar plus 4c. This is the equation. which we have to find out with the yield stress of the column. Okay, where here sigma y will be equal to yield stress on the column n phi. How we can calculate that n phi? N phi will be equal to tan square 45 plus pi by 2. We have already know that pi value is given is 50, so we can easily calculate it. Again, n phi will be equal to tan square 45 plus 50 by 2. Okay, n phi will be equal to tan square 45 plus 50 by 2. So whatever what is the value is coming. So after doing the calculation, it will come under that n phi will be equal to 7.55. You can do the calculation, you can get this value, n phi will be equal to 7.55. Okay. Now the remaining one is sigma r0 bar. Okay, what is sigma r0 bar? That is effective radial stress. And where the sigma r0, how we can calculate that formula is given is k0 into sigma v0 bar. Okay, where what is k0? K0 is nothing but coefficient of lateral pressure. Okay, its value is given taken as generally 0.6. Okay, so here we can take that value of k0 will be equal to 0.6. What is sigma v0 bar? So this is the effective vertical stresses. Okay, so how we can do the calculation of effective vertical stresses? So calculate at a depth of 4 times the diameter of the stone. We can calculate this effective vertical stress at a depth of 4 times the diameter of the stone. We know that the diameter of a stone, that is 0.9 meter. So we can just calculate what is the depth. So what is that depth for effective vertical stresses will be equal to 4 into diameter of the stone. So what is that value? Equal to 4 into this diameter of a stone is 0.9 meter. So if you do the calculation, it will come around 3.6 meter. 4 into 0.9 is nothing but a 3.6 meter. So at the from the top, that is ground level, we have to calculate that effective stress at the 3.6 meter. Okay, we'll move ahead. So this is the vertical effective vertical stresses. So you can see we have already seen this. This is our soil pad having a 7 meter. Okay, but the density of that soil is different. Why? Just because of groundwater table. So this is 7 meter, and this is a groundwater table line. So I'll just mark it. Okay. So here the density is 17.65, and here the effective density of soil is 7.85, just because of this water. This is the full of water. From here that water is available. So this is the density of the soil as well as density of water. So effective density we can calculate gamma submerged. Okay, so this will come around 7.85. So that's why you can see in this equation 17.65 into 1, and but we have to calculate that effective stress at a depth of 3.6 meter. Just we have get that value. This is a 3.6 meter. Okay, 3.6 meter. So from 3.6 meter, 1 meter is having a density of that soil is 17.6. Remaining depth is, this is nothing but a 2. This is nothing but 2.6 meter. Just because of 1 meter we have to reduced. Okay, so 17.6 into 1 plus 7.85. You can see this is 7.85. This will value will be 4 into 0.9. This is nothing but 3.6. 3.6 minus 1 will be equal to 2.6. So this is 2.6. Okay. So 17.6 into 1 plus 7.85 into 2.6, you can get that value. Sigma v bar will be equal to 38.06 kilopascal. Okay, I'll just erase it. Okay. Now, what is the effective radial stresses? Okay. So, this is effective radial stresses. So, what is effective radial stresses? Sigma R0 bar will be equal to K0 into sigma V0. Okay. So, what is the K0? K0 we have already known 0.6. We have just calculated sigma V0, that is vertical stresses, effective vertical stresses. So we'll do the multiplication. So sigma R0 effective radial stresses will be equal to 0.6 times of vertical stresses. So it value will comes around sigma R0 will be 22.83 kilopascal. Okay. Now, yield stress on a column due to bulging of column is given by this equation which we have seen in the initial one. So, we know that all the value n phi, sigma r0 and 4c. So, you just substitute n phi we have calculated is 7.55. Okay, sigma r0 here just we have calculated 22.83. Okay, we have substituted plus 4 into C. What is C? C is nothing but Cu is given in the question is 18 kilopascal. Okay, so we have just substitute these values as C. So when you do the calculation, its value is come around sigma y will be equal to 716.001 kilonewton per meter square. This is all of you this understood. This is nothing but a stress. Okay, so this is sigma y will be equal to 716.00 kilonewton per meter square. What is the stress? This is nothing but force upon area. Okay, this is not force. So we have to just convert it into force form. Then we will get it. Okay, so sigma y is the vertical yield stress over the column. So yield load, when we do that stress to load calculation, so yield load on column due to bulging of the column is given by yield load will be equal to yield stress into area. Okay, what is the area? You can see this is yield load is 700, stress will be 716 over the, this is the stone column. Okay, so this is the stone column having the area is nothing but this area. Okay, at the bottom when we can see this is a circular area. So having the diameter is d will be equal to 0.9. So when we do the calculation of this circle, so this area will be equal to pi by 4 into d square. So this is the area. So that is the area is mentioned here. So we can do that. Yield load will coming as 455.5 kilonewton. Okay, so what is the permissible load? So permissible load is yield load divided by factor of safety. Here the factor of safety is not given in the question, so you can assume that any in the question is factor of safety is given against bearing. Okay, not against yield bulging. Okay, so factor of safety will be equal to 2 to 3. Let's take it factor of safety will be equal to 2. So permissible load will be equal to 455.5 divided by 2. It will come around Q1. This is the one load. Q1 will be equal to permissible load will be equal to 227.47 kilonewton. Okay. So this is the one load which we have find. Remaining two load permissible load is remaining. So again that is calculation of resistance against bearing of soil. Ultimate bearing capacity of the soil is purely cohesive is given by Q ultimate will be equal to C into NC. Okay. So Q ultimate will be equal to C value will be equal to 18. NC value we have calculated. So NC is given in the question is 6. Okay. So that it will come around 108 kilopascal. Again, this is the stress. So we have to go for the safe. Q safe. Safe will be equal to against factor of safety. Here we can take that factor of safety will be equal to 2.5, that is mentioned in the question. Okay, so Q safe will be equal to Q ultimate divided by factor of safety. So 108 divided by 2.5, it's come around Q safe will be equal to 43.2 kilonewton per meter square. Okay, Now here we can assume that of a stone column arranged in a triangular pattern. Okay, so this will be arranged in a triangular pattern, and for the triangular pattern its value will be around 1.85 meter center to center. This is a spacing which we have to assume. This is not a correct, we will do that correct afterward. So this is the assumption which we have arranged, that stone column in triangular pattern. So total area of the stone column is given by capital A. So what is that total area? Total area will be equal to 0.866 S square. Okay. So this is mentioned in that IS code. Therefore, we can calculate that total area of a stone column. This is not a single stone column. Total area of a stone column will be equal to 0.866 times of 1.85. So 1.85 S is nothing but a spacing. Okay, a spacing of this stone column. Okay, so area will be equal to it's around 2.96 meter square. This is the total area. Now the area of each stone column is given by pi by 4 into d square. So we have just substituted that d value is 0.9. So small, that is area of a single stone column will be equal to 0.636 meter square. Okay. So area of soil surrounding of each stone column will be equal to 2.96 minus 0.63. What is actually, you can see, this is our soil mass. I'll just explain you. This is our soil mass. Okay. In between that, this is a stone column. So this is a stone column. So its effect will be, again, this is another, when we can see in the plan view. So you can see this is the one stone column. This is another stone column. This is another stone column. Here is another. Here is the third one. So this is formed in a triangular pattern. So triangular pattern. So its effective area will something around this much. Okay. So it will pass. This area is capital A. Capital A minus a small a. This is a small a. So this is the actually area of the soil surrounding of each stone column will be this one. Okay. So permissible load will be given by Q permissible will be equal to Q safe into area. So Q safe we have calculated 43.2, and area will be equal to, this area will be equal to capital A minus small a. So it will 2.324. So Q2 will be equal to 100.39. Okay. So I'll just erase it. Next, third step is calculation of resistance against the surcharge. Okay. So calculation of resistance against surcharge. Surcharge cause increase in radial stresses. Again, there is already mass of the soil, and when we have penetrate into that stone column, so it will create that additional radial stress into it. So that we will take into consideration. Okay, what is sigma r, delta sigma r bar will be equal to Q safe upon factor of safety into bracket 1 plus 2 K 0. What is K 0? K 0 is nothing but a effective stresses, which we have already know. Q safe is also we know, factor of safety we already know. So Q safe will be equal to how much? 43.2 kilonewton per meter square, and K0 will be equal to 0.6. So substitute the value and get that delta sigma r bar. So it will come around 31.68 kilopascal. Okay, sigma delta sigma r, which we have already calculated. Now increase in ultimate capacity expansion is given by this equation. Increase in ultimate capacity expansion. Okay, so N phi into delta sigma r into FQ. What is FQ? FQ will be equal to generally taken as 1. This is by basic expansion factor for clay soil. Okay, for clay soil basic expansion factor will be taken as 1. So we'll just substitute it 1. So that value increase in ultimate capacity expansion. This is again nothing but a stress. Okay, 7.55 into 31.68. So it will come around 239.18 kilonewton per meter square. Just because of a stone column, it will cause that any increase in ultimate capacity expansion. So it will 239.18 kilonewton per meter square. Now, increase in yield stress will be equal to area into increase in radial stresses. So here that area of a stone column is taken. So pi by 4 into dA square into increase in radial stresses, that which we have just calculated back is 239.18. So you can do the calculation, its value will come around 152.16 kilonewton. So this is the yield stress. uh, uh, Load will come 152. We will go for the safe side. So permissible load against the surcharge Q3 is given by this load upon factor of safety. Here again that factor of safety is not mentioned in the question. You can assume that factor of safety will be equal to 2. Therefore Q3 will be equal to this permissible load against surcharge, 152.16 divided by 2, it will come around 76.08. So this is Q3. Q3 will be equal to 76. So we have just calculated Q1, Q2 and Q3. So these all three load which we have calculated, and then we have to add it. So total permissible load is given by Q1 plus Q2 plus Q3. So therefore Q will be equal to Q1 plus Q2 plus Q3. So total load will be equal to, you can just substitute, this will around 200 something, will in the first slide. Okay, 200 something around value, it's 100 point something, and this 76 point something. So it will come around 404. Okay, now the last step, that is calculation of number of stone columns. So how much number of stone columns is required in this? So area of tank is mentioned in the question. So area of tank, the diameter is given, so we can calculate that area of tank, pi by 4 into dA square. Here the diameter of the, not the stone column, diameter of tank. Okay, so this is a 79-meter diameter of tank is given. So you can do the calculation. So its value is 44901.7 meter square. This is the area of tank. How much the load tank due to the load due to tank? So area of the tank into pressure due to tank. So pressure due to tank is mentioned in the question. Is 100 something. Total load due to the tank will be equal to that area into 147. That is mentioned in the question. That is surcharge, which surcharge not, that is effective pressure. You can see. I'll just go through in the question. You can see. Yes, you can see here the load intensity of the earthen pad is 147 kilopascal. So from there we can just calculate it. This. Okay. Huh. Yes. So we have this 147 value. So you can do the calculation. The total load due to the tank will come around 77,20,545.48 kilonewton. Okay. So number of how much the stone column, this much is the total load which is coming from the tank, and we have know that load bearing capacity, that is Q value will come around 400 something. So that will we have calculated in the previous slide. Okay, this one 404.21. This this is the single stone column load carrying capacity. So, how much the number of stone columns? Total load due to tank divided by load carrying by each column. So, the number of stone column will be equal to this value, total load, from the tank divided by Q. So, it will 72 7,20,545.48 divided by 404. It will come around 1782.6 number of columns is required. So which we have again, that is round off. So round up, we have to round up. So number of stone columns which we have provided is 1783. 1783 stone columns is provided for this. Okay, the last one is calculation for a spacing of a stone column. Okay, so again, which we have assumed that a spacing is assume that a spacing, but due to the increase of that stone column, its spacing will be changed. So initial assumption of the area of the soil per stone column, A will be equal to 0.866 s square. So area of per column will be equal to area of tank into number divided by number of column. So area per column will be equal to, so this area, that is a capital area, 49,901.7 divided by 1783. So it will come around 2.74 meter square. Okay. So equating area per column width equation, this area. Okay. So from this we have to get that value of spacing. So 2.74 will be equal to 0.866 s square. Okay, therefore s will be equal to 1.78 meter. Initially, its s will be different. So 1783, the final statement which we have written down, 1783 stone columns needs to be placed at a spacing of 1.78 meter in triangular pattern. So here we have to complete this. So this is the final statement which we have find the layout. This much of a stone columns having this spacing will be 1.783. Thank you for watching.